Hello and welcome to our Safety Smarts presentation. In this session, we will be taking a look at low voltage capacitive voltage sensors and medium voltage non-contact test probes. What you need to understand before trusting your life to these tools. Low voltage capacitive voltage sensor. Tick tracer. Glow meter. Sniffer. They go by many names, but capacitive voltage sensors are all designed to do one thing: detect the presence of voltage in a wire or piece of equipment without making direct contact with a conductor or energized part. These test tools are popular because they're inexpensive, easy to use, and small enough to fit in a shirt pocket. Capacitive voltage sensors are very handy and can quickly help you identify energized conductors without having to expose the energized conductor. Note the voltage rating of the device. Here, this one is rated for 600 volts AC. Also note that most, if not all, of these devices are only good for alternating current. They will not detect direct current DC voltages. Also, per the NFPA 70E and CSAZ 462 Field Electrical Safety Standards, you are required to test phase to phase and phase to ground when determining if a low voltage circuit is de-energized. This applies to all circuits less than 1000 volts AC. Therefore, these should not be your primary means to determine if equipment is off before working on a multi-phase circuit. What is the principle of operation behind this test instrument? The test instrument works on the principle of capacitive coupling. To understand this, let's review electrical circuit theory and recall how a capacitor works. A capacitor has two conductors, or plates, that are separated by a non-conductor called a dielectric. If we connect an AC voltage across the two conductors, an AC current will flow as the electrons are alternately attracted or repelled by the voltage on the opposite plate. In other words, there's a complete AC circuit, even though there's no hardwired circuit connection. The electrical field inside the capacitor, between the two plates, is what completes the AC circuit. Capacitors are often thought of as individual circuit components, but in reality, the world is full of small, stray capacitors you might not normally think about. For instance, suppose you're standing on a carpeted concrete floor directly under a 120-volt light fixture and the light is on. Your body is conducting a very small AC current because it's part of a circuit consisting of two capacitors in series. The two conductors or plates of one capacitor are the live element in the light bulb and your body. The dielectric is the air between them. The two conductors for the second capacitor are your body and the concrete floor. The dielectric for the second capacitor is the carpet, plus your shoes and socks. This second capacitor is much larger than the first. Understanding how the voltage divides between these two capacitors in series is critical to understanding how the capacitive voltage sensor works. Let's return to the electrical circuit theory again. In a series circuit, the largest voltage will develop across the largest impedance. With capacitors, the smaller the capacitor, the larger the impedance, which is known as capacitive reactance. Thus, when two capacitors are in series, the largest voltage will develop across the smallest capacitor. In this example, only a few volts will develop between your feet and the floor, the large capacitor, while the remainder of the 120 volts will be between your head and the light bulb, the small capacitor. Now if you hold the barrel of a capacitive voltage sensor in your hand, then place it near the conductors of the light fixture, you're basically inserting a high impedance sensing element into a capacitively coupled series circuit. Your hand, arm, body, and feet form a relatively large capacitor coupled to the floor. The sensor tip is a small capacitor coupled to the live conductor. As a result, the sensing circuit in the tester detects voltage and signals to you via a lamp, tone, ticking noise, or buzzer that voltage is present. Thus, the nicknames glow meter, tick tracer, and sniffer. Let's address limitations of this sensing technique. Will the sensor still work as designed if you are not holding it or if you are on wooden ladder? The simple answer is no. The reason for this is that you've opened the capacitively coupled circuit by removing your hand from the sensor or sufficiently isolated yourself from ground. And as noted above, capacitively coupled circuits must be closed, complete, for current to flow. Whenever the dielectric between two conductors is increased so much that the field between the two conductors is diminished to the point of ineffectiveness, the circuit opens. Another way to conceive of this is to think of the effective capacitance at that point in the circuit as becoming smaller and smaller because of the increase in dielectric. Capacitive reactance increases as capacitance decreases and continues to grow to the point where virtually all the voltage drop occurs across this now open element of the circuit. Any remaining voltage drop in the capacitive sensor portion of the circuit is now too small to activate the test instrument. In practice, this means that the capacitive sensor must have a sufficient ground connection, typically via the operator, for the tester to operate as intended. Let's address another limitation. Will the tester work on a shielded cable or through a metal enclosure? The answer is no. The tester won't work if the capacitive sensing path is interrupted by a metal shield, such as a metallic conduit or a metal enclosure. Assuming that both are effectively grounded, it can't detect voltage inside a metal enclosure, grounded metal conduit, or shielded cable. On the other hand, if the sensor does activate on a metal conduit or a metal enclosure, this indicates that those surfaces are not effectively grounded and pose a shock hazard. Now that we better understand exactly how the low voltage capacitive sensor works, we can better understand why the NFP-A70E and CSAZ 462 field electrical safety standards do not want us using this technique as a primary method of voltage detection on low voltage circuits. Now, it should be noted that the NFPA-70E and CSAZ 462 Field Electrical Safety Standards provides an exception for testing for the absence of voltage on circuits above 1,000 volts alternating current. For circuits above 1,000 volts, you are required to test phase to ground voltages. Plus, we are dealing with higher voltages to overcome the voltage drop sensitivity. Therefore, most of the test probes on the market are non-contact test probes that measure voltage from phase to ground. There are phasing sticks and other means to measure phase to phase, but typically non-contact test probes are used for the task of testing for absence of voltage. Non-contact AC voltage detectors are used to verify live or de-energized conductors. These detectors are used with hot sticks, using the splined universal end fitting. Testers indicate the presence of voltage with an extra bright LED light and a distinctive audible signal. Non-contact AC voltage detectors alarm in the proximity of electric fields. As the name suggests, non-contact voltage detectors can be used without them needing to touch the electrical supply and, instead, flash or beep when near a power source. Voltage detectors do not actually detect voltage itself, but instead detect electric fields. Electric fields are created by voltage, and the two have a causal relationship, which means that the higher the voltage, the greater the electric field. Magnetic fields are created by the current and have the same type of causal relationship as electric fields and voltage. Electromagnetic waves are emitted from sources with a voltage under load, and this is what the non-contact voltage detector senses. The internal circuit of a non-contact voltage detector leads to an antenna or sensor, which is positioned in the tip or end of the voltage detector. When the electromagnetic waves hit the antenna, a signal is sent through the circuit, which turns on the light and/or buzzer. Antenna, angle, and electric field. Maximum sensitivity is accomplished when the probe is parallel with the target. At this alignment, the maximum electric field is passing through the antenna. Sensitivity is reduced or lost when the antenna is not parallel with the target. Probing along a stress cone. As stated earlier, a non-contact AC voltage detector detects electric fields. The greater the voltage, the greater the electric field, and thus the better the measurement sensitivity. When probing along a stress cone, remember that the stress cone reduces the percentage of line voltage as you move down the stress cone. Therefore, the electric field at the bottom of the stress cone is at its lowest percentage of line voltage and has the smallest electric field. Obviously, we would want to probe near the top of the stress cone to ensure we are receiving the largest electric field. Probing along a dead break or load break. A dead break elbow requires the cable to be dead to be detached or attached and is typically rated for 600 amps. A load break elbow can be attached or detached live or under load and is typically rated for 200 amps. The ability to detach the connector alive or dead is the basic difference between these terminations. One major similarity between the dead break and load break is the semiconducting outer envelope. This outer envelope, or jacket, is made of semiconducting ethylene propylene DNA monomer rubber, or EPDM for short. Its design provides relief of electrical stress the same as the cable screen shield. Its connection to the cable screen ensures that the assembly is maintained at earth potential. Since this semiconducting outer envelope acts as a screen, absence of voltage detection at this point is not possible. Since the outer envelope jacket on a dead break and load break are semiconductive and maintain the assembly at earth or ground potential. Another similarity on these terminations is the test point. The test point is electrically protected by a cap made of semiconducting EPDM. A capacitive voltage divider enables the assembly to be checked for the absence of voltage before removing the connector. Note, the semiconducting cap must be removed with a high-voltage stick prior to making absence of voltage measurement. Since the cap is semiconductive and will act as a shield, it should also be noted that not just any non-contact AC probe will work on these accessories. The voltage test point is a capacitively coupled connection. It is not directly connected to the conductor. Not all non-contact voltage probes are designed for this task. You will need to test with a suitable sensing device, designed for use with separable connections manufactured with capacitive test points, to determine if the cable is energized. Do not use conventional voltage measuring equipment. Test with a suitable sensing device designed to work on a capacitively coupled test point. For example, the underground residential distribution or URD mode found on certain Salisbury voltage detector models have been designed to work with these connectors. In summary, performing an absence of voltage test on all electrical components and circuits is critical to the safety of electrical workers. Never attempt to touch an electrical component or circuit until you have proven it to be de-energized. Low voltage capacitively coupled sensors can be a convenient tool, but without a firm understanding of how they work, they can be dangerous and provide a false reading. Whenever the dielectric between two conductors is increased so much so that the field between the two conductors is diminished to the point of ineffectiveness, the circuit opens and the low voltage capacitive sensor is rendered ineffective. The NFP A70E and CSAZ 462 Field Electrical Safety Standards do not allow the use of a non-contact sensor to be used as a primary tool for absence of voltage readings on any circuit 1000 volts or less. Readings must be performed with a voltmeter, phase-to-phase, and phase-to-ground. The NFP A70E and CSAZ 462 Field Electrical Safety Standards provides an exception for testing for the absence of voltage on circuits above 1000 volts alternating current. When using a non-contact medium voltage probe, maximum sensitivity is accomplished when the probe is parallel with the target. At this alignment, the maximum electric field is passing through the antenna. Sensitivity is reduced or lost when the antenna is not parallel with the target. When probing along a stress cone, remember that the stress cone reduces the percentage of line voltage as you move down the stress cone. Non-contact probes and sensors do not work if the sensing path is interrupted by a metal shield, such as a shielded medium voltage cable, metallic conduit, or a metal enclosure, assuming that all are effectively grounded. Not all proximity testers will work on load break and dead break elbows. Do not use conventional voltage measuring equipment. Test with a suitable sensing device designed to work on a capacitively coupled test point. This has been a Safety Smarts presentation. Please discuss these points with your coworkers. Remember, safety is all of our responsibility.